Welcome back. Today we want to finish out the discussion of the graphs of trigonometric functions by investigating the graphs of y equals cosecant of x and y equals secant of x. So the first thing we do is remember, by definition, cosecant of x is the reciprocal of sine of x. So in a similar way that we handled the graph of y equals cotangent of x, we're first going to sketch just y equals sine of x, and then think about what the reciprocal does. So y equals sine of x starts at the midline, goes up to the maximum, turns to the midline, then comes down to the minimum and returns to the midline, and it keeps going. And I suppose I can do this for the negative values as well. Okay, so we have the maximum value is 1, the minimum value is -1, and we go pi over 2, pi, 3 pi over 2, 2 pi, and the period of y equals sine of x was 2 pi. So it repeats itself every 2 pi. Going backwards, that's negative pi over 2. This is negative pi. Negative 3 pi over 2, negative 2 pi. Now, for the reciprocal. Our goal is to take 1 divided by the value of sine of x, meaning 1 divided by the y value in this graph. So first things first. If I take 1 and try to divide by 0, I get undefined. This behavior gives us a vertical asymptote wherever the graph of y equals sine of x is at its midline. So notice we're getting a vertical asymptote every pi. Okay? Then, when I have a y value of 1, 1 divided by 1 is just 1. When I have a y value of -1, 1 divided by -1 is just -1. So the graph, which I'm drawing in red, this is going to be cosecant of x, is going to overlap with the pencil graph y equals sine of x every time I'm at the maximum or minimum. Then, if I have 1 divided by a positive number, my answer is positive. But as my positive number gets smaller and smaller and approaches 0, 1 divided by that value is going to get bigger and bigger, so I'm approaching the vertical asymptote. By symmetry, we have the same behavior on this side. Now down here, as my pencil graph y value gets closer and closer to 0, 1 divided by that is going to be negative, but it's going to be a very, very negative number. So this will happen, and by symmetry, on the other side, this will happen. Okay, so we notice that this and this put together form one cycle. So the period of cosecant of x is 2 pi. And perhaps you remember that from an earlier section where we said sine, cosine, cosecant, and secant have period 2 pi, while tangent and cotangent have period pi. Okay, cool. So there's the graph. Now let's repeat this for y equals secant of x, keeping in mind that secant is 1 over cosine. So we'll apply the same logical reasoning and say start by graphing y equals cosine of x. So we start at the maximum, and then we come down to the midline, down to the minimum, back up to the midline, up to the maximum, down to the midline. Okay, and I can continue the trend over on this side. Something like this. All right, so the maximum value is 1, minimum value is -1. We have pi over 2, pi, 3 pi over 2, 2 pi, and then 5 pi over 2. And we notice that cosine also has a period of 2 pi, so we normally think of it from there to there, from top to top. But really, I can take any 2 pi segment, and that will represent one full cycle. Backwards is -pi over 2. There's -pi, -3 pi over 2, and -2 pi at the maximum. We would like to take the reciprocal of this. So same logic as we did over here. Whenever the graph of cosine of x, so the pencil graph, is at its midline, we're going to have a vertical asymptote because 1 divided by 0 is undefined. And that type of behavior will produce a vertical asymptote on the graph. Then, wherever cosine is at 1 or -1, since the reciprocal of 1 is 1 and the reciprocal of -1 is 1, we have overlap. And then, as we did before, we will draw toward the asymptotes. and then this will continue in the other direction. So once again, it appears 1, 2 of these things put together is a full period. Just like with cosine, we have this mound and this upside down mound put together as one period, or put together as one period. There we go. So once again, the period is 2 pi. We can think of it from there to there, or we can think of it from here to here. It doesn't really matter. Any 2 pi segment you take is one full cycle. So now that we have the basic shapes of the graphs, we can talk transformations. So immediately, we can get something like this and say, first things first, take the coefficient in front of x and factor it out. That way we can do dilations first. So this is going to be pi over 6 x. Then factoring means I have to take 3 pi over 2, divide by pi over 6, and that's going to get me times 6 over pi, which will get me 9, minus 5. So this 2 right here, this will give me a vertical dilation by a factor of 2. This pi over 6 right here is going to get me a horizontal dilation by a factor of the reciprocal of this, so that's by 6 over pi. And then these numbers right here will get me a translation of 9 units to the left and 5 units down. So this information combined, we can take the horizontal dilation factor and say the period needs to be 2 pi times 6 over pi. It's always 2 pi times the reciprocal of this value. It's going to be 12. And the phase shift is -9. Tells us that we're shifting horizontally toward the left. And then the midline is going to be y equals -5. Now, to deal with the vertical dilation factor, so strictly speaking, the word amplitude is reserved for sine and cosine, so I'm not going to use the word amplitude to describe cosecant. However, in order to graph this, I'm first going to graph the sine version of this. So what I mean by that, y equals 2 sine of pi over 6, parentheses x plus 9, minus 5. So this is not the same graph as that. But we're going to argue that if we graph this first and apply the reciprocal shape, we're going to get this graph. Allow me to demonstrate. So first things first, we've got a midline of -5. So we'll start down here. Sure, -5. And then we have an amplitude of 2. And I get to say amplitude because this is a sine graph. So if I go up 2, I will be at -3. And if I go down 2, I will be at -7. Great. So my sine graph is going to exist within these dashed lines. Then my phase shift is -9, so I can go backwards 9. And let's say maybe this is about 9. So I would like to start my graph at the midline, right? Because sine starts at the midline. And then my period is 12. So I want to go 12 into the future. And 12 into the future is going to end up at +3. This is where I end one cycle and I end up at the midline again. Now there's this tactic I introduced where we say if you take the period and you chop it into quarters, because cool things happen in quarters when you're dealing with trig graphs. That's 12 over 4 is 3. So I'm going to count in 3. So it's -6, -3, 0, 3, 6, 9, 12, 15. Okay, so within that, I'm going to go from the middle up to the top, back down to the middle, down to the bottom, and then back to the middle. And so my graph is going to be shaped something like this, right? This should be very reminiscent. And I can go up to the top, back to the middle, down to the bottom, back to the middle, and then do this. And of course, we understand the graph continues forever, but we don't have the patience to really draw that much, so I'm just going to draw 2 periods and call it good. Now, number 2. The graph of y equals 2 cosecant pi over 6, x plus 9 minus 5. To get this, all we have to do is say, if we transform the sine graph like we did, then the cosecant graph, which is normally just like that on the sine graph. And I did that pretty quickly, but if we remember, this is the shape, right? If I have a sine graph, then the cosecant graph looks like this. If I move the sine graph around and transform it, the cosecant graph should transform in the same way, so that it's always stuck to the sine graph. So if I say wherever the sine graph hits the midline, the cosecant graph will have a vertical asymptote. And then wherever the sine graph hits the maximum or minimum, we're going to have overlap, and then we just draw toward the vertical asymptotes, like this. This is how the graph of cosecant works when you transform it. So reviewing the tactic once more, we're going to take this cosecant graph that we were presented. But instead of approaching it as cosecant first, we're going to deal with sine first, because sine and cosecant are reciprocals of each other. It is a lot easier for us to imagine what sine of x looks like when you transform it. So in pencil, I draw the graph of the sine transformed appropriately. Once I've drawn that, I just have to establish the same shape relationship, where I say every time the sine graph passes the midline, the cosecant graph has a vertical asymptote. And then everywhere the sine graph hits its max or min, the cosecant graph will overlap. And then from there, I draw toward the vertical asymptotes. And that completes the shape. Let's do another example with secant this time. So the first step, always, I will factor the coefficient on x out so we can do dilations first. 1/2 x minus, I'm going to take pi over 3 divided by 1/2, which means multiply by 2 over 1. It's 2 pi over 3. And then from here I can say, all right, we have a vertical dilation factor of -4, which means we're going to have a reflection over the x-axis, right? And then we're going to have a horizontal dilation based on this. So be by a factor of the reciprocal of 1/2, which is 2. And then we're going to have translation to the right 2 pi over 3 because of this, and then up 1 because of this. So once again, I'm not going to use the word amplitude to describe secant because amplitude is reserved for sine and cosine. But when I deal with the cosine graph, my amplitude is going to be 4. And I'm going to make sure to flip it upside down. So I'm going to start cosine at the bottom instead of at the top. Okay, we'll get there. And then the horizontal dilation factor of 2 is going to tell me my period is normally 2 pi, but multiplied by 2 because of the horizontal dilation, which means this time my period is 4 pi. Then the translation to the right is going to tell me my phase shift is positive 2 pi over 3. And then my vertical translation is going to tell me my midline is y equals 1. So, step 1. We're going to draw the cosine version of this. So I'm going to write -4 cosine, parentheses 1/2, x minus 2 pi over 3 plus 1. Notice I've changed the secant to a cosine. So I'm drawing the reciprocal graph first. So the midline is y equals 1. And then the amplitude is going to be 4, so I'll go up 4 from here and down 4 from here. So I suppose that looks about right. Add 4, I get 5. Subtract 4, I get -3. And then the cosine graph will live in this region right there. This is my phase shift, so I'm going to go to the right by 2 pi over 3. Perhaps something like this. And then this is going to be the start of my cycle, which means I'm going to start at the bottom. Why? Because it's a negative cosine. Cosine normally starts at the top. Negative cosine starts at the bottom. Okay. Then my period is 4 pi, so I want to advance 4 pi into the future to complete one full cycle. If I take this and add 4 pi, I get 14 over 3 pi. I'm not sure if I have the spatial awareness to get that right, but it's going to be something like that, 14 pi over 3. Okay, but good things happen in quarters, so we're going to take our period and cut it in 4. Period divided by 4 is simply pi. So every time I advance by pi, so I'm going to establish tick marks here in equal spacings, hopefully. And these will be pi apart from each other. So this will be 5 pi over 3. This will be 8 pi over 3. This will be 11 pi over 3. Going backwards, this is negative pi over 3, negative 4 pi over 3, negative 7 pi over 3, and so on. Okay. So from the bottom, we're going to go up to the middle, up to the top, back to the middle, down to the bottom, and that's one full cycle. So if I sketch it out, something like this. Shape's a little suspicious, but that's okay. And then we go back here, going backwards, I'll hit the midline there, then up to the top, then back to the midline. And if I mark one more, this is negative 10 pi over 3, I'll hit the bottom there, and that'll be one full cycle. So something like that, something like this. All right, so there is our cosine graph. But of course, that wasn't the goal, right? Our goal was to produce the secant graph. So number 2, we'll say y equals negative 4 secant 1/2 x minus 2 pi over 3. And the logic is very similar. We're going to say, because the secant graph is being transformed in the same way as the cosine graph, because we established the same set of transformations, the secant graph should appear stuck to the cosine graph in the same way as the original did, if you remember over here. Right? So this was the cosine graph, and the secant graph was stuck to it like so. So the logic, wherever the cosine graph hits the midline, the secant graph will have a vertical asymptote. And notice here, right, the vertical asymptote is going to occur every half a period. So every 2 quarters, you get a vertical asymptote. And then wherever the cosine hits its maximum or minimum, the secant is going to overlap. And then finally, we just take this and we draw toward the vertical asymptotes. Something like this, something like this, and something like this, something like this. And there we have it. That red graph is the graph of negative 4 secant, parentheses, 1/2 x minus 2 pi over 3, all plus 1. Same tactic. So, despite the excessively squiggly lines and perhaps scary-looking graphs, at the end of the day, the logic that governs how to graph trig functions is all very consistent. Right? So it came down to saying y equals f of x by default. So this f of x could represent sine of x, cosine of x, tangent of x, cotangent of x, cosecant of x, or secant of x. We have 6 different graphs. And the deal was, we said y equals a times f of, and we put a b here, x minus c plus d. And in order to understand this in the way we did in lecture 5, you saw me consistently factor out the b, coefficient on x. And from this position, we say, okay, so this a is going to give us the vertical dilation factor. And this was going to affect our amplitude. In the case of sine or cosine. And strictly speaking, the word amplitude is reserved for just sine and cosine. Everything else, we don't use the word amplitude. We just say vertical dilation factor. But we can understand that the A is stretching the graph vertically. And then we said there's a horizontal dilation governed by this B. And this is going to give us a horizontal dilation by a factor of the reciprocal of that number. And so we understand that the period is a horizontal thing. The period is going to be the default period multiplied by 1 over b. Now the question is, what is the default period? Right, the default period was 2 pi for sine of x, cosine of x, cosecant of x and secant of x. Extend this down here. And then it was pi for tangent of x and cotangent of x, right? So if you're dealing with any transformation of these graphs, your period is going to be 2 pi times 1 over b. If you're dealing with either of these graphs, then it'll be pi times 1 over b. And then we said this c over b right here is going to be a translation toward the right. It's going to be right by c over b. And then this right here is going to give us an up by d. And this idea said, oh, so the phase shift is c over b. And this tells us we're going to move to the right or the left if c over b is negative, and that's going to be the starting point of our graph. So if it's cosine, we're starting at the top. If it's sine, we're starting at the middle. If it's tangent, right, we're starting at the middle. And if it's cotangent, we're starting at a vertical asymptote. Those last two you might have to think a little bit about looking at the graphs. And this d is going to be a vertical translation, so that's going to give us the midline. The midline y equals d. And ultimately, we can take this information and, number one, take an equation and make a graph out of it. Number two, take a graph and make an equation out of it. Now, of course, I'm personally not interested in making you take a graph of tangent, cotangent, cosecant, or secant, and then write an equation for it. I think that is much less applicable to what we want to do in life, and I will focus on sine and cosine graphs, which we're calling sinusoidal graphs. Yeah? So for our last bit, let's put all of the trig graphs on one sheet of paper and call it a day. Y equals sine of x. So this one is going to start at the midline. It's going to go up to the maximum and then return back to the midline. Come down to the minimum, return back to the midline. And cool things happen in quarters of a period. So that's going to be pi over 2. That's going to be pi. That's going to be 3 pi over 2. That's going to be 2 pi. The maximum value of normal sine is 1. The minimum value is -1. So the range is from -1 up to +1. And just for fun, we'll do another period going backwards like this. Something like that. All right. Y equals cosine of x. So cosine of x is going to start at the top, at its maximum value of y equals 1. And this is going to come down to the midline, down to the minimum, back to the midline, and then back to the maximum. And that's going to be one full cycle. This feels oddly asymmetric. We'll do something like this and call it good. Okay. Then over here, it's going to return to the midline here, then go to the minimum value, then return to the midline over here, and then go back up towards maximum value. Minimum value, of course, is -1. And cool things happen in quarters of a period. So that's going to be pi over 2. That's going to be pi. That's going to be 3 pi over 2. And then all the way out here is going to be 2 pi with a full period. And then going backwards, negative pi over 2, negative pi, negative 3 pi over 2, and then negative pi. Negative 2 pi, sorry, back here. Same deal. Okay, we've got it. Now, the next thing we did was y equals tangent of x and y equals cotangent of x. And this is where we introduced the vertical asymptotes. So we said y equals tangent of x starts at 0. It's going to reach 1 somewhere, and then at pi over 2, it's going to have its vertical asymptote. Now this somewhere is going to be half of pi over 2, which is pi over 4. Going backwards, at negative pi over 4, tangent is going to reach -1. And then at negative pi over 2, it will have another vertical asymptote. And then cool things happen in quarters of a period. The full period is 1 pi, so every quarter of a pi we will reach an interesting point here, an interesting point here, an interesting point here, and a vertical asymptote over here. Similar business on the other side. Midline here at negative pi, up here, and down here. And of course, the shape we just sort of connect through like this. So the tangent graph is going to have vertical asymptotes at every odd half pi. And it'll hit the midline at every integer pi. Now cotangent of x, which was the reciprocal of tangent of x, in this case, perhaps it helps to draw it separately instead of just trying to draw both graphs on the same set of axes. So we said with cotangent of x, we're going to have a vertical asymptote right through the y-axis. And then cool things happen in quarter of a period, so pi over 4, pi over 2, 3 pi over 4, and then full pi. We hit a vertical asymptote at the full pi. Going backwards, negative pi over 4, negative pi over 2, negative 3 pi over 4, negative pi. We hit a vertical asymptote at negative pi. And then in between, we're going to hit the cool points, midline right here, positive 1 up here, negative 1 down here. Midline in between the asymptotes, positive 1 over here, negative 1 over here, and we just connect the dots. So with cotangent of x, we see that the vertical asymptotes occur at the integer pi's, and you hit the midline at the half or the odd half pi's. Now finally, let's go back up to here and say, now we can graph y equals cosecant of x and y equals secant of x. These are the reciprocals of y equals sine of x and y equals cosine of x. So the logic was, wherever sine hits the midline, cosecant has a vertical asymptote. Wherever sine hits the max or the min value, cosecant overlaps. And then we simply draw toward the vertical asymptotes, and that gives us the graph of y equals cosecant x. Same logic over here. Wherever cosine of x hits the midline, secant of x is going to have a vertical asymptote. Wherever cosine of x hits its max or min value, secant of x will overlap. And then simply draw toward the vertical asymptotes. And because of this relationship, it is much more advantageous for us to draw cosecant and sine on the same axes, secant and cosine on the same axes, whereas tangent and cotangent, we might want to separate them just because of the way they're laid out. So this is everything all in one. And from here, all you have to do is remember how to transform properly, and you can graph any variation of any trigonometric function. Well, thanks for tuning in, and as always, please practice. This is the kind of thing that the more you practice, the easier it gets. Take care.